Hello, today we're moving from DC circuits into the world of alternating current. I'll be solving my B-level task, problem 18 from Randall's, which is about an RC high-pass filter. I use the Prada model to explain my logic and verify it using the Volstad circuit simulator. So let's start with pattern recognition, because this problem contains a classic trap. Like in previous DC circuit problems, the pattern was simple. You just add the voltages together, like in DC, if the source voltage is 15 volts and the capacitor takes 5 volts, the resistor would take 10 volts, because it's simple math. But here I recognize a new pattern for AC circuits, because the current is alternating the voltage across the capacitor and the resistor are out of phase by 90 degrees. The pattern here is a right angle triangle, meaning we must add voltage like vectors using the Pythagorean theorem and not regular numbers. So next is decomposition. I break the problem down into the 3 vector components of my triangle. It's actually called phasor when we're turning the graphic into vectors. So let me draw a phasor. The angle between voltage of capacitor and voltage of inductor is 180 degrees, but since we don't have inductor, we just delete this. And we have resistor. Here we have 90 degrees, and source voltage will be like this. It depends on the value. So here is simple math. If we will move and I mean this is capacitor and like this, and there's a V source voltage, and our formula will be V resistor square plus V capacitor voltage capacitor square equals voltage source square. So the hypotenuse is a peak source voltage, and one side is a peak capacitor voltage. The missing side is a peak resistor voltage. So now I apply abstraction. The problem mentions it's a high-pass filter, but I don't need to know the specific AC frequency, the capacitance, or the resistance to solve for the voltage. I can ignore those physical details and abstract the circuit purely into its geometric voltage vectors. So let me go to the algorithm part. Just solve this problem. Here we'll just use this formula, and here resistor voltage will be equal to V source square minus V capacitor square, and we have all the values, like 15 square minus 5 square will be equal to 200 root of 200. That will be equal to 14.13 volts. So now let me show you. To prove this, let's look at the Volstad simulation. Let me build it faster. I will just use, like from circuits, I'll use high pass filter RC. Let me delete this. Let me add what we have. Actually, let me delete only this one. Oh, I choose the wrong one. So let me delete this one, and now I need to add voltage, source voltage with 2 inters, and that's it. Now I need to add a wire. So now let me build a circuit. Okay. So now we have a simple circuit, serial circuit. Since we only know this value, like our maximum like source voltage is 15, and let me change the frequency to 50, and we don't know actually the numbers, the values of capacitor and resistor, so we need to just tune it by ourselves. Let me show its graphs. So yeah, here the capacitors, or I mean, yeah, capacitors voltage is 15, it's too much. So let me add some value. Let it be 100. Yeah, it's still, let me add some resistor, like 90. It's still not changing, right? Yeah, now we have like, now we have those values, like our maximum. So let me slow this one. Now our maximum source voltage is 15, like how it's given in the task, and our voltage, capacitor voltage is 5, and we can notice that our resistor voltage here is 14.14, how we get in the answer. So so you can like see at the oscilloscope graphs and notice that the peak of the capacitor voltage and the peak of the resistor voltage do not happen at the same time, and this phase shift is exactly why 13.1 volts plus 5 volts doesn't equal to 15 volts. The simulation perfectly confirms my vector mass. So using Prada helped me recognize the phase shift pattern and avoid the trap of simple addition. And that's it. Let's move to the next problem. So now let's look at my challenging task, problem 47. We have a parallel RC circuit. This is a big step up from the B-level problem. So here you can see a very important pattern here. In my first task we had a series circuit, so we used the phasor diagram to add voltages. Now I recognize the opposite pattern in a parallel circuit. So voltage is the same for everyone, but the currents are different. So I'll apply the Pythagorean logic, but this time for currents instead of voltage. Like we had a series in previous task, series circuit, so our voltages were not same, like and in this one, in parallel circuit, voltage are the same, but it's not a big deal. We can just use since currents are not same, we can draw a phasor by using currents. It would look like for voltages, the phasor would look like this one. They would be the same because they are same. But for currents, let me use. There's a same principle like resistor current, capacitor current, inductor current, and between inductor and capacitor current there's 180 degrees always, and we don't have inductor current, so we'll just use only these ones. So in decomposition part, I decompose the circuit into the two independent branches. The resistor branch where the current follows Ohm's law, like resistor current will be just equal to Ohm's law, which we already know. And the capacitor branch where the peak current depends on frequency and capacitance. E0 capacitance resistor, which is 1 divided by omega capacitor. So our formula will look like this. So yeah, that's it. So for abstraction, I use abstraction to simplify the math, even though the actual currents are fast-moving cosine waves. I treat them as frozen vectors in a phasor diagram. This allows me to use simple geometry instead of complex calculus. Like this phasor, I'll just, how I said before, I treat them as frozen vectors in a phasor diagram. And in algorithm part, we can easily see that again that Pythagorean logic will just calculate the hypotenuse using the Pythagorean theorem. I0 I source will be equal to square root I resistor square plus I capacitor square. And then we can easily find it because we know the formula for resistor and capacitor currents. And it will look like this: E0 square resistor square plus E0 square omega square capacitor square, and we can take out of the branches, out of the square root E0, and there will be left only resistor square plus omega square C square. And that's it. So let me show it in the simulation. You can like I already built the circuit. You can see that like let me start it actually. Reset and started. So from here you can see that the total current and the branch currents, if you look at the scope, you'll see the total current is larger than resistor and capacitor individually. But it's not a simple sum of the two. The vector math we just did explains exactly why. So let me use our formula that we get from here to prove that this one is real. So let me stop this. And what we have, let me use this formula. Like we need to find I. We have E0 from here, 100 volts. Let me put it. And we have resistor, which is 90 ohms, 90 squared plus for omega we have frequency, and we already know the formula for omega, 2p frequency and multiplied by capacitor, which is this is squared, which is 10 minus 6 also squared. And we can just simply for frequency we use 50 hertz. And let me use my calculator here. Okay, 100 square root 1 divided by 90 squared plus 2 pi f squared, and yeah, and we got 1.11156 amperes. So let's check it now in the graphs. We got source current, so we need to check in this graph because it's all about source. So here we got the peak current, and we need to check the yellow one. Let me use the yellow one is all about current, the green one is about voltage. So here from the peak you can see that the peak current is equal to 1.109 amperes, and it's exactly the same that we got here. So we can say that we proved the answer, and using Prada helped me recognize the phase shift pattern and solve this problem. So that's it for today. Thank you for watching.